In today's video, we are going to take a look at hypothesis testing with a specific goal of better understanding the logic behind what is called null hypothesis significance testing. And you'll often see this abbreviated to just NHST, null hypothesis significance testing. And this is what a lot of science and psychology is based around. And I'm a psychologist, so I'm going to talk specifically about psychology. But this is when you hear phrases like P is less than 0.05. That's what this has to do with. And really, the way that we build out and think about null hypothesis significance testing is you start with a null hypothesis. This is abbreviated to HO. And what the null hypothesis states is that there is no effect. And so you can think about this like a correlational study, that there is no correlation, or like an experimental study where there's no differences between the experimental group and the control group, or a quasi-experimental study where you're looking at maybe the differences between people of different races in income or something like this. So you compare two different races on income. The null hypothesis is going to say that there's no difference between people of different races on income. Now, what the researcher proposes and tests in null hypothesis significance testing is what we label as the alternative, and oftentimes you're going to hear this referred to as the research hypothesis. The alternative hypothesis. And essentially this one states that there is an effect. And so if we're thinking about like the null hypothesis here, this would say that your correlation R is equal to 0. And really, we wouldn't actually write R is equal to 0 when we're thinking about this. What we would use is because, and this is a little bit above the scale of a traditional intro to psychology methods course and statistics course, but we write our hypotheses based on population parameters is what these are called. And then to test hypotheses, we use a sample, because remember, we are using our sample to make generalizations about the population. Now, our sample uses the sample statistic R. Actually, the population parameter for R is the Greek letter rho. And so actually, when we're writing out our hypotheses, we would write rho is equal to 0. But again, a lot of my students in intro level statistics are thinking about R values when you think of a correlation. So the null hypothesis would state that there is no significant effect. If you were doing an experimental study where you're comparing your experimental group to your control group, this would basically say that the experimental group is equal to the control group. In other words, mean 1 is equal to mean 2, because you're taking the average of group 1 against the average of group 2. The population parameter that we would use is actually the Greek letter mu. So it looks like an M, but it's sort of a weird looking M. And we would say mu1 is equal to mu2. The experimental group is equal to the control group. Now, the alternative hypothesis, the way that we would write this, is that R is, we could either write it as not equal to 0, and you could also write that the experimental group is not equal to the control group. You could do it that way. If this was, so this is for correlational research, and this is for experimental. And quasi-experimental would just be that group 1 is not equal to group 2. It would be very similar to the experimental. You could also make a directional prediction where you say R is greater than 0 or R is less than 0. Again, I should be using population parameters of rho, but for my students, I want to use R because that's how you're thinking about correlations. I realize that we should phrase our hypotheses in terms of population parameters rather than sample statistics, but for an entry-level course like what this video is intended for, it's much easier to envision R values because that's what we talk about a lot in class. Here we would say that, another way of phrasing this using a directional prediction is that the experimental group is greater than the control or less than the control. And so what our study is doing is, and the whole premise for how null hypothesis significance testing works is it asks this question of, do we have evidence against the null? Now, oftentimes, if we have evidence against the null, scientists will take that to mean that probably it's due to the reasons outlined in the alternative hypothesis. Now, that being said, there is a little bit of a jump in logic here, and that's why null hypothesis significance testing has been criticized for decades, is that saying that we have evidence against the null hypothesis is not the same as saying that we have evidence for the alternative hypothesis. And I realize that there is a little bit of a jump in logic there. To be honest, null hypothesis significance testing has been critiqued for a long time. There are other forms of statistic like Bayesian statistics and things like this that sort of work in a slightly different framework. That being said, a lot of science still operates and will continue to operate using null hypothesis significance testing. But again, this is the big question that we are asking, is do we have evidence against the null hypothesis? So at this point, I very frequently ask my students, is I say, okay, is our sample perfect? And they always readily say, no, our samples are not perfect. And I say, okay, so let me just kind of draw out a possibility here. So if the null is true. So let's say that this is a correlation possibility ranging from -1 to +1 because that's the possible values for a correlation. And the null hypothesis is right here in the middle saying that R or rho is equal to 0. And then I come back, I say again, is our sample perfect? And my students say no, our sample is used to make an estimate of the population. And so if I were to run this study with, say, 200 people, which is a pretty adequate sample size for a correlational study, if I was to run a study with 200 people and try to make a generalization to the population, am I going to find that R is exactly equal to 0 every single time I run that study if the real population value was 0? My students always think about that for a little bit, and then they say, no, you probably aren't going to get exactly 0 every time, even if the population value was exactly equal to 0. And so what that means is that sometimes I'm going to get a value here, sometimes here, every now and then probably way out here, but it's probably more unlikely. And that's what we're doing here statistically, is what is the likelihood of finding a correlation pretty far away from 0 if the real population value is 0. Well, the further that your R value is from 0, so the further we get in this direction or the further we get in this direction, the more evidence we have against the null hypothesis. Because if I found a correlation of 0.9, well, it's probably fairly unlikely that the real population is 0. I'm going to say that again. If I ran my study with 200 people and I found that two variables were correlated at 0.9, is it very likely, based on my sample statistics, that the real population correlation value is 0? No, because if the real population value is 0, I would expect to find something close to 0 most of the time. Now, am I going to find exactly 0? No. And what we would expect is just by chance, it's going to form a little bit of a normal bell curve shaped distribution. Is that sometimes I'm going to find values here, sometimes way out here, and maybe every now and then I do find a correlation way out there, but it's highly unlikely that I would have achieved a value way out there, again, if the null hypothesis was actually correct. What happens is null hypothesis significance testing uses probability to make a judgment. that if I find a value, and I'm going to actually switch colors here, that if I find a correlation way out here, well, it probably did not come from this distribution, meaning it probably is not correct that the real population value is 0. Instead, the real population value is probably somewhere in this distribution. It's basically saying that once we get far enough in this direction or in this direction, we start to have evidence against the correlation value coming from this distribution, and we're saying that it's more probable that it came from one of these two distributions. And that's how this p is less than 0.05 thing works, is that this is a probability of finding a test statistic as extreme, meaning far away from 0, as far away from 0 as you did, if the null is true. So it's basically saying that if the null is true, what's the probability that you would have found a value clear out here? And I'm going to circle that. If the null hypothesis is true, what's the probability that you found a value clear out there? Well, it's probably fairly unlikely, which would mean that my p-value would be quite low. And I want to just do something just real quick here. So in my classes, I always tell my students to hold their hands like this. And I always tell them to write on one hand, test, and I'll do this with you, statistic. So I always write test stat on my hand, and then I write p-value on the other hand. What happens here, and I say, students, put your hands together like this, and we do this about 30 times between this point and the end of the semester. And I say, as the test statistic gets more extreme, meaning that your test statistic gets further away from 0 in either direction, as it gets further away from 0 in either direction, your p-value decreases. So as your test statistic gets more extreme, your p-value decreases because they are inversely related. And this is true about basically every test statistic out there, whether it's f, p, t, chi-square. As it gets further away from 0 in either direction, now not every test statistics can be negative, but they all work. As they get further away from 0, your p-value decreases. Now we've heard these words, statistical significance. When is something significant? Well, something is significant when p is less than 0.05. So when your test statistic gets far enough away from 0 that your p-value, which is a probability again of finding a test statistic as extreme as you did if the null is actually true. So that's basically saying if the real population correlation is 0 and you found a correlation of 0.5 in your study, well, 0.5 is fairly far away from 0, which means that p has dropped quite a bit. The p-value is probably less than 0.05. So you would do what's called rejecting the null hypothesis. In that case, you would say there is a significant effect. So what you're doing here is when we use this phrase, reject the null hypothesis, what you are essentially saying is that I have evidence against the null hypothesis in favor of the alternative hypothesis. I have evidence against the null hypothesis, so we do what's called rejecting the null hypothesis. We say, I would reject the null hypothesis and say that there is a positive correlation. Or I would reject the null hypothesis and say that I found a negative correlation. This is saying that we have evidence against there being no effect. And I know that's a little bit of a double negative going on there, so I'll say it again. When we find a significant effect, we are saying that we have evidence against the null hypothesis being true. Now, in real scientific writing, we tend to just use the language of there is a significant effect or there is not a significant effect. But again, behind the scenes, the logic of null hypothesis significance testing is that we either found a significant effect or we did not find a significant effect. And finding a significant effect, again, means that p is less than 0.05. We found a significant effect. So let's actually practice just for a little bit. It's always good for students to practice at this point. Let's say that I ran a study and my p-value was equal to 0.623. Would that be significant? The answer is no, because 0.623 is greater than 0.05. We only reject the null hypothesis when p is less than 0.05. What if my p-value was equal to 0.069? Would this be a significant effect? The answer is also no, because 0.069 is greater than 0.05. What if my p-value was equal to 0.027? Would this be a significant effect? The answer is yes, because p is less than 0.05. And for a lot of students, this is really simple, comparing 0.05, comparing 0.027 to 0.05. But a lot of students do struggle between, like, is it significant if it's greater than 0.05? Is it significant if it's less than 0.05? Remember, it's only significant if your p-value is less than 0.05. And then some people move the decimal. Like sometimes I'll be like, what if my p-value is 0.006? They sometimes say no, because they're thinking 0.06 instead of 0.006. But this would be yes, because it's much less than 0.05. It's actually a whole decimal point less than 0.05. This is in the thousandths place, whereas the 0.05 is in the hundredths place. So you do need to just kind of practice, and it becomes automatic, actually. You get really, really good at looking and interpreting p-values across time. Now, I do want to talk about a couple of things here at this point. Is one, what if you see that the p is less than 0.001? Because this is how you will very frequently see p-values reported when there's a high level of statistical significance. This is less than 0.05 for sure. This is usually associated with a fairly strong effect when you see this. But p is less than 0.001. What this is telling you, and the reason, because a lot of people when they first start writing this, a lot of stats programs will actually just show you p is equal to 0.000, and a lot of students will report it like this. This is not how we report it. This would mean that you had proven your effect. But as we discussed earlier in the semester in all of my classes, we don't ever prove anything, because with all science, there's a possibility for error. And the reality is that somewhere along this line, maybe it's 0.0000000, there will be a number. There will be a number. Your p-value is never, ever, ever exactly equal to 0. And so we always do round p-values to 3 decimal places. And so we always use this type of notation when it is less than 0.001 to indicate that you haven't proven anything, but you have maybe potentially a high degree of support for that hypothesis there. So I also want to talk about the language that we use. So we either reject the null hypothesis, or we say fail to reject. This is the two types of language that we use. Now, a lot of students would default to saying that we accept HA or we accept HO. And this is the language that a lot of students sort of adopt early on in their thinking. But these two things are not equivalent. This is not equivalent to this, and this is not equivalent to this. I want to come back to what we're doing here, is that our study and our statistics that we use is asking, do we have evidence against the null hypothesis? Now, what this is not asking is, do we have evidence in favor of this? It's not saying that. It's asking, do we have evidence against it? That is not at all testing, do we have evidence in favor of it? The other thing that it's not doing is it's not asking, do we have evidence in favor of this? It's asking, do we have evidence against the null hypothesis, or do we not have evidence against the null hypothesis? That's the question that we're asking, and this is the logic behind null hypothesis significance testing. It's a very important type of understanding that we need to wrap our head around. Now, whenever we run a study, it actually creates 4 different outcomes when we run a study. So we've got to think about this. What is the true nature of the world? And what did we find? Meaning, what did we conclude in our study? Now, whenever we are thinking about drawing conclusions from a study, we hope that the results from our study match what's actually true about the world. But this is asking, is there a significant effect in the real world? Is there an effect? And is there an effect? Now, obviously, we would love to find what is true about the world. So is there really an effect in the real world? The answer could be no, or the answer could be yes. What did we find? Did we find that there is an effect? No. Did we find that there is an effect? Yes. And these are the 4 possible outcomes that could happen when we run a scientific study. Now, I always ask my students, when did we find the correct thing? And they always say, right here, we found the correct thing. And down here, we found the correct thing, because the yes is matching up with the yes, and the no is matching up with the no. Right? So these are the two situations in which we drew the correct conclusion. Now, all science has the possibility for error. There are times that we say, no, there's not an effect, when actually there is. This is called a type 2 error. And this is what we refer to as a miss. This is when we ran a study, we did not find a significant effect, but we should have found a significant effect. We should have rejected the null hypothesis, but we didn't. Now, this is potentially due to the way that we ran the study, but oftentimes it's just due to random chance. That sometimes we are going to miss the effect even if it's there. Now, one of the things that often leads people to missing an effect is called low power. This is when your sample size is not high enough to detect a significant effect of the magnitude that you might expect. We definitely do not want low power in our studies. For a correlational study, and I'm teaching a class on correlations, which is what this video is typically assigned for. With a correlational study, to have adequate power, you need to have about 200 people in your sample to have adequate power in most correlational studies. Now, down here, what has happened here? Well, we said that there was a significant effect, but in reality, there wasn't. This is a type 1 error. This is a false alarm. It's kind of like the boy who cried wolf, right? Where we are saying that there's a significant effect, but there is actually not a significant effect in the real world. Both of these are bad. We don't want to be here. We don't want to be here. But I always ask my students, and I want you to try to answer this question on your own right now. Just kind of pause the video and answer, do you think that a type 1 error is better, or do you think that a type 2 error is better? And actually what you should be asking yourself is, which is worse, a type 1 error or a type 2 error? Is it better to miss the effect, or is it worse to miss the effect, or is it worse to say that there's an effect when there isn't? So pause the video and think about that for just a little bit. So the worst of these effects, by far actually, is a type 1 error. A lot of my students actually say at this point that a type 2 error is worse because they think about all the time and the resources that we invested into trying to find this effect, and then bam, the results say no, there's not a significant effect, and they say, damn it, we didn't find the effect. And I'm going to be honest, that happens to me too. When I run my analyses and there is no effect, I say shit. But I want you to think about what actually gets published and what actually influences the world. In my classes, we talk early on in the semester about what is called publication bias. What are people motivated to publish? Are they motivated to publish studies that support the hypotheses or don't support the hypotheses? In other words, if I ran a study on a new drug and maybe it was going to fix some kind of cancer, and I run this study and I design it, I put a lot of effort and time, and I seek out a grant, I get good grant funding for this, I put years of time into this, and then it doesn't actually cure cancer. Are people going to publish it? Well, probably they won't get as excited about it as if I said, wow, look at this new intervention, this new drug that totally cures cancer. Probably not as excited, right, when it doesn't work. And so the reality is most of the time type 2 errors don't actually get published because that's you saying that you didn't find an effect. There's a positive effect bias in psychology and all sciences where people are very motivated to publish studies that, quote, work, that support the hypotheses. And so oftentimes the only studies that get published or the only errors that actually make their way into the publication and the published world are type 1 errors. Some folks would actually argue that type 2 errors make science better. And that's sort of based around the idea that scientists are at least somewhat arrogant. And I don't want to say that scientists are narcissists and stuff like that because I am a scientist, right? But the idea behind type 2 errors potentially making science better is based on this idea that if someone goes through all of this effort to try to test a hypothesis and then finds no effect, do they just give up right away? Probably not. The argument that some would make is that not only do they not give up, they think and ask this question, why? What did I do wrong, essentially? So how could I make my measurement better? How could I make my setting more controlled? How could I better test this research question? And some people would actually argue that a type 2 error makes science better because it forces scientists to think about what did I do wrong and how could I improve my study. Now, I'm not going to go clear to that point. I do think type 2 errors are more negative than they are positive, but I do understand that argument there. But by far, the worst type of error in a research study is what we refer to as a type 1 error.